Hey everyone, thanks for stopping by. My name is Bryan Hughes. I work at a small startup in San Francisco called Speakeasy, where we do a bunch of open API kinds of things there. One of the things we do is we actually write a lot of Go code there. And sometimes we even use it from WASM for various performance reasons. And I've also done some other work on performance in the past. And so today I want to talk about performance ultimately. So another performance about Rust and JavaScript and more than that. There's been a lot of talk in the industry. We've been celebrating a lot of new tools, things like that. And I often see this getting framed as, we rewrote this thing in Rust and it's 100 times faster. And Rust is a great language. We can do a lot with it, but there's more to the story going on as we can possibly, I'm sure you can imagine. So today I want to kind of dive into that some and see, where do these languages help? How do they help? Where's kind of a better place to use it? And what else is going on too? As much as we can in 30 minutes anyways. But to kind of start about what really got me thinking why we're all talking about it is that in the JavaScript world, our tooling has become blazingly fast. Where we are now versus 5 years ago is just, we're in a radically different world. We have all kinds of new tools that have come out that's in some ways changed the way we do development even. So just a quick overview of a couple of these. These are just handpicked. Sorry to the projects I don't mention. There's a lot of other good ones. But first, the Speedy Web Compiler. So this is a JavaScript transpiler. It takes in TypeScript, JSX, the latest versions of the ECMAScript spec, and converts it into something that browsers across versions can actually run. We've been doing this kind of transpilation for at least 15 years, maybe longer than that. So the concept isn't new. But now we're starting to write in new languages. So Swick is written in Rust. And it kind of replaces Babel, which is written in JavaScript. And it is up to 70 times faster than Babel. That's almost 2 orders of magnitude. That is huge. Similarly, which we heard a little bit about this morning, is OXLint, which is a JavaScript linter, also written in Rust, meant to replace ESLint. And it's about 100 times faster than ESLint. So this is 2 orders of magnitude. And these are really big. It's not just that it's faster, right? It's so much faster that we can start to envision new workflows around it, things we couldn't think of before. We can think of performance-intensive linting rules that are actually doable now, whereas in the past they would have slowed VS Code to a crawl. You would have hit one keystroke and 30 seconds later you might get a result. But now we can make them feel almost instantaneous. So it opens up new possibilities. And I think this is so exciting. Another thing that's been in the news that I'm also really excited for is the rewrite of TypeScript. The TypeScript team is rewriting TypeScript from JavaScript in Go. And their early tests show that it's up to 12 times faster. Now, that number, compared to the previous new numbers we saw, might be a little underwhelming. This isn't 2 orders of magnitude. This is closer to 1. But this isn't because the folks working on TypeScript aren't really good engineers. They are. And it's not because Go is a slow language. It's a fast language. But there's just more going on here. And so I kind of want to go into that. So what is part of a language, and what is coming from other types of optimizations, perhaps? So first, let's do some level setting. I'm going to talk about some benchmarks that I wrote for this talk so we can really understand specifically the role that these languages play. So the setup for this is I wrote 4 programs in JavaScript, Go, Rust, and C. I use the exact same algorithm in all of these to make sure we're controlling for variables. So I'm not using different types of approaches that might be faster. We're getting an apples-to-apples comparison. And of course, I ran the same data in all of these. So we're going to start with something really easy. Basically, it's kind of a little warm-up algorithm. We're going to do bubble sort, right? The kind of classic thing that we learned when we're first starting to code, and then immediately forget about because no one should ever use bubble sort. It's slow. But this is the code for it. We can see it in all 4 languages. It's pretty much exactly the same code. We're initializing memory in the same place, so allocations look the same. This is about as apples to apples as you can get. Some of these may not quite necessarily be semantic. I tried to avoid those where I can because there's some weird things. For example, in Rust, there's a swap function you can use to swap the value of 2 variables. Turns out it's really slow. So who knew? Turns out, though, this is a really good apples to apples comparison. We run this code and we get exactly the kinds of results that you would expect. There's nothing at all interesting with these results. Almost don't want to show it because it's boring, where we have Go as the slowest language out of these, followed by JavaScript, and then Rust, and then C. OK, so obviously this is not what we'd really expect. So what's going on here? So in JavaScript, I'm running this inside of Node.js, which means we have the V8 JavaScript engine. And inside of V8, it has an optimizing compiler called Turbofan that does just-in-time compilation. And it has a couple of different levels. The idea is once it starts to see like, oh, I'm getting a feel for the code you're running, I'm seeing the similarities, I see the kinds of data you're passing through it, and it makes assumptions about the future that you're probably going to keep doing the same thing. And as it gains more and more confidence, it kicks into higher and higher levels, with the highest level being where it actually is compiling machine code and executing it just as if we wrote C++, compiled it, and ran that. Now, I've actually never seen this in the real world before. This has always been theoretically possible. But here, we kick into that highest level of JIT, and we just never leave. Right? So this shows how, this is the absolute fastest JavaScript can be. And basically, here's proof, which is really cool. But of course, this is not at all real world, least of which is that it's bubble sort, which is, again, slow. So JavaScript is doing well relative to the others. But look at that scale. We're sorting 100,000 15-bit integers. And it's taking 5 seconds for JavaScript to do this. Go is 7, and nothing is sub 1 second. This is a horrendous amount of time. But we expect this because this is bubble sort, and bubble sort is slow. Again, no one should ever use it. So instead, let's look at radix sort. Now, I'm not going to show the code for this because this is starting to get more complicated, and the details actually don't matter that much. If you're curious about the algorithm, you can look at it online. But it's really optimized for this kind of algorithm, or for this kind of sorting. So if we look at the results here, we get this. We're starting to look a little more normal. OK, JavaScript is now the slowest, with Go, Rust, and C in that order of performance after that. Now, this is still pretty fast. It's still a very simple algorithm. We're still kicking into the highest level of Turbofan, but we're starting to see more of what we'd expect. But the other thing to point out again is look at that scale. Now, instead of taking several seconds, we're taking just a few milliseconds. This is 1,000 times faster than the previous algorithm. So if you take the slowest version of this compared to the fastest version of the other one, it is just a night and day difference. But all right, OK, this is still very, very synthetic, right? This is not real world at all. So let's look at something a little more real world than that, and that is AST parsing, right? This is something we actually do all the time in our tooling. So AST parsing is where we take the contents of a file of source code, and we convert it into this like in-memory semantic representation so we can then analyze it. This is the first step in basically any tooling we do where we're going to, say, bundle stuff together or do linting or formatting, any of that. That all starts with an AST. Now, I was not about to write a JavaScript AST parser in all 4 languages. That would have taken me all year. So I created just a tiny little toy language. And I wrote a very simple parser for it. For the language nerds out there, I wrote what's called an LO1 recursive descent parser. If you don't know what that is, don't worry about it. It doesn't really matter. What's important is that this is an algorithm with a bunch of recursion in it. Pretty much every single node. And if you think about it, however many characters there are in a file, there's usually almost that many nodes most of the time. So there's recursion for every single node. And there's a ton of conditionals. It's like switch statements everywhere. And this kind of code just isn't quite as JIT friendly, but also starts to look a little more real world. In JavaScript, we're not usually doing number crunching. We're doing a lot of conditionals, figuring out what to do. And so when we look at the results of this, this is starting to get in line with our expectations, where JavaScript took 4 milliseconds, Go was just a hair over 1, so Go is 4 times faster, with Rust being faster than that, and C at half a second, with C being 8 times faster than JavaScript. And this is like fairly real world, actually. Most of the time we see speedups will be more than this. This is still a little synthetic, but this is reasonably representative. But of course, we are here at JSConf, right? We're all JavaScript developers, and especially a lot of us who work in the browser, we can't just run this code. When I ran these benchmarks for C, for example, I used Clang to compile it to a binary, and I ran that binary from the command line. Right? That's not an option, especially in the browser. So this is where we have to look at starting off in JavaScript and then going over to that language using WebAssembly. Right? This is a really common technique, and it's one of the really exciting technologies. It's one I really love. So for this benchmark, I did the exact same thing as the previous benchmark. And this code and this data, it's like exactly the same. But I start off in Node.js, where I have Node.js read in the file from the file system, and then passes the contents of the file as a string across the WebAssembly bridge into Go, Rust, and C, where it does the actual AST parsing. And then it sends that AST data back over into JavaScript, which is a pretty standard way of using WebAssembly, right? And the results are terrible, as it turns out. So the thing that's going on here, like the trick with WASM is these languages, I mean, they all work differently, and they represent data very differently. So like a string in C is just a byte array, for example. Sometimes there's fancier classes in C++, but in C, it's literally a byte array. It's just like a uint8 array buffer inside of JavaScript. Obviously, that's not how we represent strings in JavaScript, though. We have encodings and text encoders and all kinds of things like that. And so that representation needs more intelligence. So when we go from one language to the other, we actually have to convert between the two formats. And this is typically referred to as marshalling and unmarshalling. We can also sometimes call it serialization and deserialization, depending on technique. Now, that's just strings. Like, strings are simple, you know. Let's think about a complicated object, something like an AST, where we have all kinds of nodes, and each node has a different type. That gets really, really difficult to translate between these languages, especially JavaScript and Go that have garbage collectors in them, and Rust and C that don't, right? There's just so much difference there. So how do we do that? Well, for this example, I'm doing a common technique, but not particularly optimized, which is in Go, Rust, and C, I JSON stringify the results, send them back across the bridge, and in JavaScript, we do a JSON parse. Right? This is a pretty common technique, but it is slow. JSON parsing just happens to be really slow. And so in each of these algorithms, the actual ASC parsing is still much faster than JavaScript, but whatever gains we have just get completely eaten up by that serialization and deserialization. And that's just something we have to contend with in the WASM world. So let's kind of bring all of these numbers together, and let's look at the actual speed up we see. So this chart shows speed up of each of these 4 languages across our examples versus JavaScript. And by speed up, I mean a value of 1 means it's exactly the same. A value of 4 means it's 4 times as fast. A value of 0.5 means twice as slow, and so on and so forth. And we definitely see a lot of trends in this data. So we see, first of all, that we consistently see different performance characteristics across 3 languages. Go is always the slowest, and C is always the fastest. But you know, at the grand scheme of things, they're sort of similar. But the other thing we see that's also consistent is that the more complex the algorithm that we're running, the greater the speed up we get from doing it in Rust and Go and C versus in JavaScript. So a couple of key takeaways from this is that, first of all, if we're thinking about writing something in a different language, the maximum amount of speed up that we can expect to get is going to be around an order of magnitude, give or take. Right? It depends on the language being ported to, and it depends on the algorithm. In certain cases, we can get above an order of magnitude, but you're not going to get much further past this. And in some cases, it may only be a factor of 4 or 5. And this is pretty consistent. I have seen this research elsewhere, and it's also, and we saw in these examples. But again, at the very beginning, I was talking about that speed up. You know, Swick was 75 times faster. Oxlent was 100 times faster, right? That is way more than this. So there was a lot more going on with those projects than just simply switching to that other language. But you know, we've looked at some benchmarks for what is ultimately still simple code, still may not be quite that real world. So I want to talk about a actual real world case study, and this is ESLint import analysis. So over the last couple of years, I've been kind of playing around with an idea, and earlier this year, I released an actual plugin that you can download and play with that has a lot of performance to it. And what do I mean by import analysis? So this is where we're actually looking at imports in your code base, and we're looking for issues. This could be things like circular imports. Is this export used anywhere else in your code base, or is it actually dead code that isn't being flagged by an unused variable or stuff like that? And these are also pretty tricky to implement rules. So let's go through it. So the premise when we're doing this is before we can analyze anything, we have to parse the entire world. In order to know if an export is used anywhere in the code base, we have to check every other file to see if it's being imported. Right? There's this relationship between files, and we can't just parse files independently when we're doing import analysis. But there is a catch to this. In ESLint, plugins run exactly once and are synchronous, which means when the ESLint comes in and says, like, hey, it's time to run your rule for unused exports or something like that, right? So in this world, it says, hey, run on this file, but it's synchronous. We have to stop everything and figure out what's going on, right? There's no notion of running twice. There's no notion of an initialization step. And we can't do stuff asynchronously to do kind of the more typical, well, I'm just going to go off to the side and do this. So the solution, if you can call it that we all do is, yeah, we just stop the world. And that rule comes in, we synchronously go read every single file in the project. We read it from the file system. We then parse it into an AST, which, as we've seen, is kind of can be expensive. And then we create this map, and then we go on linting. What this also means is in ESLint, we are actually reading every file from the file system twice and parsing it into an AST twice, because ESLint also does this. But again, because of the ordering, we can't take advantage of what ESLint does. So it's not a great solution, but it's what we all do. But it also means that there was a bit of opportunity. Since we read in files and parse them on our own, we can play with that part of it and look for some speed up. I'm not going to talk about everything I do in that plugin. That's not really the point of this talk. I just want to give one example of an optimization that I did, and that has to do with module type determination, which I just realized I have a spelling error in it. Joy. So in this, whenever we're reading in code, we are analyzing your project. And when we're doing this, it's like we only care about your own code. We're not going to go in and lint everything in node modules, right? That would be silly. And it would take forever. So we kind of got to know whenever we're importing something, is this our code or is it someone else's? And of course, also, is this something built in, like the FS module in Node? So here's how I do it. And I do it actually kind of backwards, as maybe a certain someone just pointed out. So Node.js actually just gives us a list of all its modules. You can just query it in this built-in modules thing. So we're like, hey, is this import sets, right? The import foo from bar that's a string. Like, is that in this array of 30, 40, whatever it is, items? Super easy. We say yes or no on that. If it's yes and it's built in, we stop. Then no, we say, hey, does this thing start with a period? If so, we know it's going to be a first-party import, because that means it's a file path. Unless someone is, say, doing a relative import into node modules, but please don't do that. That's a very bad idea. But then it still could be first-party code. Like, we're not done yet. A lot of modern systems use aliases. So like in Next.js, by default, you can import from like @/components/mycomponent. It's actually a first-party import. We have to specify it. But again, that list of aliases is a very short list. Like, we can read it into memory, and we can tell that. And then if the answer to all of those questions is no, then we just know, hey, this is third party. It's kind of like process of elimination, we get to third party. And the reason I do this is this can be done completely in memory. Never have to touch the file system, never have to read any packaged JSON files, and it can be really, really fast, whereas all the other approaches are generic resolvers that read from the file system all the time. But I'm not just doing algorithms. I am also using Rust in this demo, or in my plugin. So I use OXC, the oxidation compiler, which piles OXLint. It's written in Rust, and I call it from WASM. And so with these things all together, we end up with results that look like this. So for ESLint plugin import, running on the VS Code codebase, which, as you can imagine, is a pretty large codebase, it takes about 70 seconds for these three rules: the no unused exports, no cycle, and no unresolved imports. Unresolved means you're trying to import something that doesn't exist. So about 70 seconds for that. There's a fork of ESLint plugin import called importx that adds a few optimizations that comes in a little over 50 seconds. My project takes 2 seconds. So that is a speed up of 35 times faster, which I think is really great. Like, I love the way this is going on. But I will say, we have Jordan Harbrand right here, the lead maintainer of ESLint plugin import, and I'm curious your thoughts.
It's great to see things getting faster. But for example, if you want to go back a slide or two, there we go. This is not a completely accurate algorithm, for example. So like Node has a feature where you can use the imports field and you can self-reference built into Node. And this, you'd have to read the package JSON on disk to support that. The first-party alias thing is, some things use that pattern, but then there's Babel plugins and TypeScript config and so on that can give you different resolution. So if you're willing to accept those caveats, then totally this works great. But if you want to make a universal and generic tool, this is the reason the import plugin has a plugin system. I didn't author this plugin originally, so but I've been maintaining it for about 10 years. So people have their own custom ESLint import resolvers so that they can resolve like things for Vue or CSS or HTML, and there's custom parsers for all these things as well. So just like Evan was saying this morning, how roll down was super fast until they realized they needed plugins, and then it wasn't super fast anymore. There's a lot of things like that where, like Bluebird was a popular promise library before promises were really ubiquitous in JavaScript. And Bluebird is faster than built-in promises, but it also doesn't comply with the spec. And if you make it comply with the spec, it's not faster. And similarly, like rollup is really fast, but it runs the risk of deleting code that shouldn't be deleted. And if you account for those problems, it stops being really fast. So it's like, what do you have any thoughts on like how you could account for all those caveats and maintain some of the performance improvements?
Yeah, those are very good points. And I totally forgot about the Bluebird promises being faster. Oh, that takes me back. And yeah, Jordan brings up some great points here. And like, I absolutely did make compromises in this. And they're actually listed out in the README. And I'm saying, like, if you're doing these things, don't use this package. And I actually even implemented a couple of lint rules that look for this behavior where I know the algorithm's not going to work to try to steer people in the right way. But like, this is a thing that happens a lot when we're doing performance optimizations. Like, some stuff to remember is that if we're really trying to get good algorithms, we have to make compromises. Right? If we need to have wide compatibility with the ecosystem, we oftentimes can't take a lot of those optimizations. And it comes down to like, what's your use case? Performance is really important that way. Also, big thank you to Jordan. Jordan is awesome. He wrote ESLint plugin import, TC39 member, a bunch of other stuff in the ecosystem, so he's great. And another point about the thing that I did, though, is Rust ended up contributing almost exactly 50% of the performance improvements. Like all those algorithmic speedups I did had about a 6% or a 6-factor increase, and Rust was also about a 6-factor increase. 6 times 6 is 36, which is what we saw. So what have we learned through all of this? So radical performance requires new algorithms. Like if we're trying to get something that's faster, not just shaving off, solving pain points, but the kind of performance where we can actually enable brand new workflows that were previously impossible, we have to have newer algorithms. We can't just do languages. But a fast language helps in these new algorithms. It can play a really big role sometimes. Right? It depends on what we're doing. Like if we're having to go through WASM, there is a lot of caveats, and sometimes this can just be kind of a rabbit hole that ends up leading nowhere. So you have to be really careful with that, which is to say it all kind of depends. Right? There's no easy answer to the case of performance, because like silver bullets only exist in fiction. Right? We want to say like, oh, let's rewrite this thing in Rust and it's going to solve all our problems. And well, maybe. Or we want to say, hey, we're going to switch to this new UI framework, move away from React, and that'll solve all our problems. Maybe. Right? It just depends. It always depends. But like, why do we have these stories? We keep seeing these stories. I feel like every new cycle we go through, like when React first came out, we're like, oh, this is going to solve all our problems. And it certainly solves some. Same thing with our new tools. They're going to solve all our problems. Well, it's certainly going to solve some, but not all. It's because like, we expect our stories to be simplified and buzzworthy. Like we like our simple stories. We like those things that catch us in the algorithms. Those things where we just like dive in. We know that's going to be exactly what we want to do. It's going to solve everything. It's going to be easy. And excuse me one moment. Sorry about that. Seems even on stage, I can't escape notifications. They're just everywhere. Like, what's going on? The truth is, like, we live and breathe a world of distractions. Like, we're constantly surrounded. We have Slack notifications all the time. If I had the default Slack notifications on, I would have been pinged 30 times this talk alone. We have deadlines we have to meet. We're also constantly on social media. We're talking to people. We're in this ever-connected digital world that never gives us a moment to think. And if we think about like the solutions, like that module resolution algorithm I showed earlier, that was an inversion of the typical way we would think about it. That wasn't some idea I came up with with profilers on and doing debuggers and stuff. It was a creative moment. I think it was like while I was out for a walk around a park. But we have to have those space, and we never give that to us. So if there's any real piece of advice that I can give is take some time to unplug. Like disconnect from technology, no phones, no laptops. Take time to just think about problems. And don't be like, I need to solve this in 5 minutes. Just think about it. Like no outcomes and let your mind wander. That's how we actually come up with these solutions. And this isn't just true of performance. This is true of like anything in engineering, product development, and anything really. The same thing with like creating art. It's all about like just sitting with our thoughts and being patient with our thoughts in the process and being patient with our brains and ultimately getting creative. Like every performance increase I had in my plugin came from some creative insight, some moment of inspiration, right? It wasn't just sitting there slogging through code. Like this is how we really do great performance improvements. With that, I want to thank you all for listening.